Algebra. Algebra? Linear algebra? What is algebra? What is linear algebra? Can I do algebra? All these questions and more in today's lecture of All right, everyone, what's up? Welcome to linear algebra. So we're going to get started. We're going to begin with Rn and Cn, that is the n copies of the real numbers and n copies of the complex numbers, and just in general, some of the most archetypal examples of vector spaces, which are the central object of study in linear algebra. We'll get to what vector spaces are in this video. We'll talk about it later. But the first thing we need before that is we need fields. Fields are the elementary algebraic object from which vector spaces are born. There are a couple of different ways to look at it. You can see fields as like the simplest type of vector space, or you can see vector spaces as being built out of fields or defined relative to fields. But whatever perspective you choose to take, fields are necessary to start talking about vector spaces. So let's begin with one of the nicest fields I know of, and one field that you are all probably well familiar with, which is the complex numbers. Now, since you've probably already seen the complex numbers, most people deal with the complex numbers in like high school, so let's not spend too much time on it. But complex numbers, which I'll use C to denote, in your book it uses a blackboard or a boldface C. I'll use a blackboard C, since I can't reliably write bold with a marker, it's perhaps more common notation. So this fancy looking C is just to distinguish it somehow from like another C, since uppercase and lowercase C's look relatively similar. So a complex number, an element of C, is just an ordered pair AB of real numbers, where we'll write that as A comma B, and then this weird symbol means in. And then this boldface R right here refers to the real numbers. Once again, I'll write that similarly to C as an R with an extra line in it, like a blackboard R, because I can't reliably write boldface with a marker. So we'll denote these pairs as A plus BI. You've probably all seen this. And the central thing about complex numbers is that we basically added an additional number called I. That number squares to -1. It's the square root of -1. And so when we multiply that by something, you get stuff, and then you can add things to it. And so we'll write all the complex numbers as A plus BI. But you can just as well think of them as ordered pairs. So the set of all complex numbers, like we said, is C, which is just the set of all A plus BIs for AB real numbers. Addition and multiplication are defined exactly as you would expect. You add the part that's not next to the I together, and then you grab the part that is next to the I, and then you add that together. We call the part that's next to the I the imaginary part, or at least the coefficient on the imaginary part right there, and then the part that is not next to an I is the real part. The multiplication is the part that's interesting. You can just straight up define multiplication in this way. So A plus BI times C plus DI is AC minus BD plus AD plus BCI. And you can get this also just from specifying that I squared is equal to -1 in the following way. That is, if you just treat these guys like regular nice old polynomials, with I being the variable, subject to this nice little relationship right here, then as you've probably seen before, but I will write out really quickly, you recover this rule down here. So just write it out really fast. Let's do it. Okay. A plus BI times C plus DI is equal to, well, just carry it on through. A times the whole quantity C plus DI plus BI times the whole quantity C plus DI. Okay, fair enough. Just distribute it on through. Now I have AC plus ADI plus BCI plus BDI squared. Now, using the fact that I squared is -1, if we're going from this route, then just group everything together, and I'll get an AC minus BD, since this guy right here is -1. Okay, and I'll put that in parentheses. Then I'll have the piece that's next to an I, which is AD plus BC. And I'll pull that I out right there. And wouldn't you know it, AC minus BD, AC minus BD, AD plus BC, AD plus BC. Look at that. We got it. Okay. So complex numbers, if you haven't seen them in a little bit, hopefully this is a nice refresher. They've got all the nice usual properties that you would like. Addition is commutative. You can do it in any order. Multiplication is commutative. You can do it in any order. It doesn't change anything. Addition is associative. If you've got two plus signs, it doesn't matter which one you do first. Okay, fair enough. Same with multiplication. You're going to multiply three things together. It doesn't matter which pair you do first. Identities, 0 is a complex number, and if you add it to stuff, nothing happens. Similarly, 1 is a complex number, and if you multiply stuff by it, nothing happens. There are additive inverses. Pick an element of the complex numbers. There is another complex number you can add to it to get 0. There are multiplicative inverses. So for everything other than 0, there is a unique element such that if you multiply them together, you get 1, the element that doesn't do anything when you multiply stuff by it. And finally, multiplication and addition play well together. You take a complex number and you multiply it by a sum, then you get the sum of the multiples of those things. Okay, cool, easy enough. We've all seen these. These are basic arithmetic rules. We've been drilling it in you since you were, probably in elementary school, I guess. So hopefully everyone has seen this in some capacity before. So a little bit of notation, and this is kind of a good way to start thinking about how we'll begin to abstract some of these things to get at vector spaces and things like that. But first, fields more generally, is we'll use some symbols. So we'll let minus a denote the additive inverse, or minus alpha denote the additive inverse of alpha. That is, it is whatever the complex number is, that unique complex number that exists, as we've specified. There's an additive inverse. It is whatever that one is, such that if you add it to alpha, you get back 0. Okay. Then if you just write it like this, notice you could write beta minus alpha just as a shorthand for saying beta plus the additive inverse of alpha. Okay, cool. So really we don't need like a separate minus operation. We just need addition and a notion of additive inverses to define something that looks like a minus. Okay, cool. Same thing with multiplication. We'll use 1 over a, or occasionally I'll write it as a inverse, a to the minus 1. We'll let that denote the multiplicative inverse of alpha. Oh, I keep saying a instead of alpha. Looks the same. But notice this only holds for alpha not equal to 0 since you can't, divide by 0, right? Okay, so it's the unique complex number such that if you multiply alpha by it, you get back 1. Same thing as what was going on up here. Easy enough. And so we can define division in this way. Beta divided by alpha is just beta times the multiplicative inverse of alpha. Okay, cool. So we don't need a separate division. It's just defined in terms of multiplication and multiplicative inverses. Nice. One other little piece of notation, if you take an alpha in, I've written this as F. We have not yet introduced fields. We'll do that momentarily. For alpha in, let's say C for now, C. And m a positive integer, we'll define alpha to the m to denote the product of alpha with itself m times. So if you take alpha times itself m times, then we'll write that as alpha to the m. So let's just leave it like that for right now. This will let us get away from some of the confusions that can come from complex multiplication. And we'll adopt this notation more generally, just in arbitrary fields, which we'll talk about next. So let's get to it. All right, so fields are basically just abstractions of the complex numbers, or real numbers if you prefer, or even rational numbers, something like that. Think of the reals. Think of just regular old numbers, regular old arithmetic. Fields are basically just sets that have two binary operations, which we will write as addition and multiplication. They don't really have to be. They're just ways of taking pairs of things and associating them to single things. Okay. And these are just two operations. We write them as addition and multiplication, ways of taking pairs of things, sending it to a single thing. And that it is a field if it works like the regular numbers. So we're basically just going to say exactly the same properties we said just a moment ago for the complex numbers here. When we said, look at all these nice properties, we're going to say that again now, but abstractly. So we'll have a set F. I'll write that as a blackboard F, so an F with two lines through it. Then a set F with two binary operations is a field if the following properties hold. First of all, let's zoom in a little bit, make this a little easier to read. Addition and multiplication are associative. That is, if you have two plus signs, it doesn't matter which one you do first. And if you're multiplying three things together, it doesn't matter which pair you multiply first. All right, cool. Just like in the complex numbers, the addition and the multiplication commute. It doesn't matter. Oops, I kind of made that hard to read. It doesn't matter what order you do it in. All right. There are distinct additive and multiplicative identities. That is, there's an element which will call one. It doesn't actually have to be the number one. It's just like a instructive name. It just is something that behaves like one relative to the operation that we're calling multiplication. So there's something which will use the symbol 1 to denote, not necessarily a number. And this thing, if you do the multiplication operation with it, doesn't do anything. That is, if you multiply anything by it, you get back whatever the thing you started with was. Similarly, there is an element which will use the symbol 0 to denote, such that if you add it to stuff, it doesn't do anything. So these are the multiplicative and additive identities of the field. And the distinctness part here, the distinct additive and multiplicative identity part, is just a requirement that they are not the same thing. The reason we care about this here is to prevent us from having things like the following. A field with just, say, a single element, let's call it E, where E plus E is E, and E times E is E. This is the most boring possible kind of object. It doesn't have anything interesting going on at all. It might as well not even have any operations being done since they don't do anything. They're both just, nothing happens, right? This is not like a bad object. It's just boring. And it will basically ruin a bunch of statements of theorems if we allow this to be a field. It's the only additional thing that ends up happening if 0 is not equal to 1. It's not like there are big extra other weird fields, but if you include this one, you get this kind of pathological example that you have to then specify you're not talking about. That is, you then have to make statements like, let V be a vector space over a field with at least two elements, which is an annoying thing to say every time, especially since we'll never want to talk about this field in the first place because it's boring. So we say, let's at least have two elements. All right, enough about that. Next up, there are additive and multiplicative inverses. Just like in the real numbers, just like in the complex numbers, you can take any element of your field, find another element, which we're just using the symbol minus a to denote, and this element is such that if you add it to a, you get back the additive identity. Similarly, if you've got an a that's not equal to 0, there's some element which I'll call a inverse, a to the minus 1, such that a multiplication operation, a inverse, is equal to the multiplicative identity. All right. So far, to be clear, these are just stand-in symbols. I'm not saying that this is minus 1 times a or something like that yet. I am not making any sort of claim like that at this point. It does, in fact, turn out to be the case. But for right now, we are just saying it is a symbol. It is just a way to specify that there is an element defines relative to a, such that if you add it to a, you get back the additive identity, and the same for multiplication. Okay, so you've got the existence of additive and multiplicative inverses. Finally, multiplication and addition play well together. You can distribute multiplication over addition. Nice. All right, cool. So do you see exactly what I'm saying with just take the properties of the complex numbers and then just, strip out the parts that refer to the complex numbers specifically and you get the definition of a field. Neat. Fields are basically the simplest type of vector space possible. We'll define vector spaces momentarily, but let's do a slightly more familiar thing first. So you've probably seen this type of thing in your first linear algebra class. That is, if you've looked at vectors at all before, you've probably seen lists of numbers, right? These like long lists of numbers. Maybe you write them with square brackets or something. And this, to you, probably maybe seems like the prototypical example of a vector, and in many ways it is. And this is really just a fancy way of trying to take a field and build something that's like a field out of a few copies of it. So if you take n a positive integer, we're going to define f to the n for a field f to be the set of all ordered lists of n elements of f, that is, all lists x1 through xn, with xi an element of the field. Here we can make addition component-wise. That is, if we take two elements of fn, so x1 through xn plus y1 through yn, what we'll do is we'll just define an addition on fn using the addition of f. We'll just add each piece together. First thing gets added with the first thing, x1 plus y1, and so on, all the way down to the last thing being added with the last thing. Nice. So fn kind of inherits the addition from f. Now, the place where things start to get interesting, and I think this is a part that is often not well motivated when people introduce vector spaces, is that you can't do the same thing with multiplication without losing some very nice properties. So here's what I mean. What about multiplication? Can we define x1 through xn, that list, times the list y1 through yn to just be x1, y1 through xn, yn? The answer, of course, is sure, but we lose a nice property, mainly multiplicative inverses. Here is the essential idea. Here's the example. So let's take 0, x2, all the way up through xn, where the rest of them can be whatever you want. This guy does not have a multiplicative inverse. Notice we do have a nice notion of a multiplicative identity. That is, if you take the list of length n whose every component is, every entry in that list is equal to the multiplicative identity of the field, and you multiply with anything in this way, then you would just get back exactly the thing you multiplied it by. So we have a nice version of a multiplicative identity, but something like this does not have a multiplicative inverse. Even when xi is not equal to 0 for some I in the set 2 all the way up to n, i.e., we have some x not equal to 0 with no inverse with respect to multiplication. So do you see why that would be? That is, this guy, there is nothing, if I'm doing multiplication in this way, that I can multiply its first component by to get 1, because 0 does not have a multiplicative inverse in a field. Ooh, that is the big problem. So can we get some other notion of multiplication? Maybe there's a different way that n copies of a field can inherit multiplication from the field so that we keep our nice properties. Yeah, we can kind of do it. Here's the answer. So the answer is scaling. First, a tiny piece of notation. I should have mentioned this before. In Fn, we're going to let 0 denote the list of all zeros, which is the additive identity of Fn. And we're going to let minus x denote the additive inverse of a list of length n in Fn, right? A list x of length n. So that's the element such that if you add it to x, you get back the list of all zeros. Okay, cool. Since we're just doing it component-wise for addition and nothing breaks down, since there are no elements that lack additive inverses in a field, that is, there's no requirement that a not be equal to something right here, right? So there's nothing that goes wrong with the addition part of it. It's just the multiplication part. So since that's all good, we have additive identities in n copies of a field. We have additive inverses. Everything's fine. But multiplication breaks. So here's how we fix it, I guess. We define it relative to elements of the field instead of lists of field elements. So for lambda, an element of the field, we're going to define lambda x for x, an element of Fn, n copies of the field, to just be the list of length n where I have multiplied each entry in the list by lambda. Okay, cool. So I'll just do it relative to a single copy of f. All right, and this, it turns out, will fix things. We'll get into that momentarily, but first, let's define what a vector space is, because we'll show that it fixes things more generally than just for Fn. We'll show that it fixes things for anything that ends up working like Fn. That is, for anything that is a vector space. Let's get into it. Okay, so vector spaces, the central object of study for linear algebra, what we've all been waiting for. So, vector spaces will work kind of the same way as what we did for fields. That is, we will basically take what we just talked about for Fn and we will abstract it. So we'll talk about an addition on a set V. This is just a function that assigns pairs of elements, which we'll express as u plus v, to each uv in V. Okay. Then there's a scalar multiplication. It's just a function that assigns an element lambda v to each lambda in the field and v in the set V. Okay, cool. So just to be clear what I mean by an addition and a scalar multiplication, since I will say that now when I define a vector space. A vector space is a set V along with an addition on V and a scalar multiplication on V, which, notice, the scalar multiplication is defined relative to a field or with respect to a field. So this is, some people will write an F vector space to specify what that field is. Okay, it's just a set with an addition and a scalar multiplication relative to some field such that the following properties hold. Okay, the first one is easy. We keep seeing it pop up. It is commutativity. It doesn't matter which order you do this addition operation in. Okay, the next one is also nice. We've seen this pop up many times before. Associativity. If you've got two pluses, it doesn't matter which one you do first. And same for multiplication. You got two multiplications, doesn't matter which one you do first. And this holds for everything in the set V and all scalars in the field. That is field elements that we're using with our scaling operation. Okay, cool. Next up, another familiar thing, an additive identity. There is an element which we're just using the symbol 0 to denote. It does not have to be the number 0, the list of all zeros, or really anything that remotely looks like a 0. We're just going to use the symbol 0 to represent it. And it's just the thing that if you use the addition operation, it doesn't do anything. All right. Additive inverses, same as before. For every element in our V space, the V part of it, it's the set V, the vector space bit, there is a W such that if you add it to V, you get back the additive identity, which remember we're using 0 to represent. There is a multiplicative identity with respect to the scalar multiplication. That is, if you take the multiplicative identity of the field and you scale a vector by it, then you get back that vector. Finally, distribution. So scaling plays well with the addition of the vector space. If you scale a sum, that is the same as summing the scales. And if you sum in the field and then scale, that is the same as scaling and then summing in the vector space. Notice these two are different pluses. One of them is an F in the field right here. The other one is in the vector space. Kind of cool. So there we go. That's a vector space. It just abstracts the properties of Fn. And as we'll see, there are many vector spaces other than just lists of field elements. Though maybe I will not give too many crazy examples quite yet. One quick little bit of a definition, or at least notation, nomenclature. The things that are in a vector space, the elements of the set V, we'll call those vectors or sometimes points. Here's a good example, like as it should be. Fn, since we're building our vector space here to be basically Fn, just with all the reference to Fn stripped away. Fn is a vector space for any field F, as it should be. Okay, here's another thing that is also a vector space, F infinity. So all sequences of elements in F, that is also a vector space. If you don't believe this, I encourage you just to kind of think about it for a moment and ask yourself, is there anything that would break if I had a very, very, very long list in Fn? Not really. And if it just kept going, nothing breaks there either. If you don't believe it, convince yourself of it. It's a very good, easy exercise. Kind of tedious, but you should go through and verify it if you don't believe it. But notice that is not a simple list of elements. It is a infinitely long list. Ooh, that's kind of weird. Here's another thing. So we'll use this notation. For a set S and a field F, we'll let F to the S denote the set of all functions that send the stuff in S to field elements. Okay, so if we define the sum of two such functions, which remember, a function is defined by what it does. If we define the sum of two such functions to be the function that sends x to f of x plus g of x, which are well defined because f and g are functions. All right. And the scaling by an element of the field, lambda times a function, to be the function which sends x to lambda times f of x, which is an element of the field. Then we've made f to the s, the space of all, the set of all functions from s to f, into a vector space. If you don't believe this, I encourage you to go through and double check it as well. This might be something that you would see on a homework, for example. Okay, cool. This is also a vector space. Notice this could be very crazy. So for example, take s to be like the real numbers and f to be the real numbers, then this is the set of all possible functions from the real numbers to the real numbers. That is a very, very, very large set. They don't even have to be continuous. They don't have to be differentiable. They can be insane and super unwieldy. Yet all the same, it is a vector space. Incredible. All right, here's a kind of nice thing to think about. So this example, I claim, and this example are kind of the same. Maybe not 100% the same, but similar at least. That is, this later example is basically a more general version of this first one. So notice a function f in f, and I'll take s to be the set 1 through n, is basically just a list x1 through xn, i.e. f of I is equal to like xi, right? That is like every function of this form specifies a list and vice versa. So in that sense, the first example is basically the exact same as this last example, or at least implied by this last example. Taking s to just be 1 and so on and on and on forever, and it's not stopping at n, then we get, I'll say f infinity here, 2 also. So that's kind of neat. All right, so this last one actually covers all of that first one. Kind of cool. Let's start proving some properties about vector spaces, and let's show ultimately that they kind of fix the problem that comes up with addition. All right. Let's prove that the additive identity of a vector space is unique. So, how are we going to do this? I've already got the proof written right here, so you can see it right there, but let's talk through it. So if we take 0 and 0 prime to be two additive identities in our vector space, what we're going to show is we're going to show that they're the same thing. So first off, just since they're additive identities, well then 0 plus anything is that thing, and 0 prime plus anything is that thing. Okay, cool. Now, in particular, if you plug in 0 prime right here, you get back 0 prime. And if you plug in 0 right here, you get back 0. Okay, look. So I've got 0 plus 0 prime and 0 prime plus 0. Hey, addition is commutative in V. So 0 plus 0 prime and 0 prime plus 0 are the same thing. So hey, would you look at it? 0 prime equals 0. And that just comes from commutativity and the definition of an additive identity. Bada boom. Maybe I should write here that this is equal to 0 prime. All right. Hopefully that makes sense. Let's try to do another one. Here, let's try another one. So, the additive inverse of any element in a vector space is unique. Let's do this. Same kind of idea. Take W and W prime to be two different additive inverses, or not necessarily different, two different ways of writing an additive inverse. We'll show that it's ultimately the exact same thing, but we're not supposing that yet. Just take two additive inverses of an element V. Then notice that W, one of those additive inverses, is certainly equal to W plus 0, since 0 is the additive identity. All right. Well, 0 is equal to V plus its additive inverse. That is the definition of an additive inverse. If W and W prime are additive inverses of V, then W plus V is equal to 0, and W prime plus V is equal to 0 as well. So I'm just going to take this 0 right here and replace it with V plus W prime. All right, cool. And now I'll use the associativity of addition to just flip my grouping of parentheses. So instead of doing this one first and then adding that here, I will instead add W to V. Okay. And hey, would you look at that? W plus V is yet again 0. And now I have my W prime sitting over here. And 0 plus W prime, well, 0 is the additive identity. I get back W prime. So would you look at that? W prime, same thing. Huh. So if you take two different additive inverses, we have just shown that they're not different. That is, if you have two additive inverses, if you write down W and W prime saying, hey, these are additive inverses of V, you have written down the same thing twice, just with two different symbols representing the same thing. So the additive inverse of any element in a vector space is unique. The fact that it works for any element is because we didn't put any conditions on what V could be. It is just an arbitrary element from our vector space. All right, cool. What do you think? Hopefully not too bad. Let's see if we can go a little bit further. So, given a vector space V, we're going to write minus V to denote the additive inverse of V. So we've said this before, but I'm just trying to remind everybody that right here so far we are still just using this as a a purely notational matter. We are not yet claiming that minus v is equal to minus 1. That is the additive inverse of the additive identity of the field scaling the vector v. We are not yet claiming that. This is purely notational, so not yet. Let's see if we can get to proving that. So to get there, we'll need to do a little tiny step. So first off, we're going to say, hey, for all v and v, if I scale v by 0, that is by the additive identity of the field, then I get back the additive identity of the vector space. That's kind of nice. If I scale by the additive identity of the field, I get back the additive identity of the vector space. All right. So by distributivity, we have the following. Here, I'm gonna switch colors so it doesn't seem so monochrome. Okay, so first off, scale v by 0. Well, hey, 0 is certainly equal to 0 plus 0, since 0 plus x is equal to x for any old x in the field, right? That is, it is the additive identity. Okay, cool. So certainly if I put in 0 for x, I still get that this statement is true. So 0 is equal to 0 plus 0. Okay, cool. So I could scale v by 0 plus 0. And hey, by distributivity, this is 0v plus 0v. Nice. All right. So combine with the definition of an additive inverse. Now we'll take, okay, 0 is 0v plus the additive inverse of 0v. That is the definition of an additive inverse, right? Whatever the thing is that is the additive inverse of 0v, which we do not yet know is 0. Whatever that thing is, if I add it to 0v, I get back 0. Okay, cool. So 0v plus the additive inverse of 0v, but I know that 0v is equal to 0v plus 0v, so I can replace 0v with 0v plus 0v. Okay, cool. And I still have that additive inverse floating around over there. So this guy's just carrying on through. All right, sweet. And now I can do a little bit of grouping. I'm skipping a step right here. If you don't see it, what I'm doing is I'm basically changing up my parentheses. So if you want, I could write this as follows. I could put these guys in parentheses right here. See, that's what I'm trying to say by my underlining. And then I could regroup my parentheses. So I have 0v plus the quantity 0v plus minus 0v. That is plus the additive inverse of 0v, whatever that thing is. Okay, I could regroup my parentheses, right? Just do some associativity. And then, by the definition of additive inverses, this piece right here is 0. Okay, cool. So I get 0v plus 0, where 0 is the additive identity of the vector space now, not the additive identity of the field, right? Okay. And so from the fact that 0 is the additive identity of the vector space, we know that this here, and this is the step I skipped, gives you 0v. So 0 is equal to 0v. Huh, cool. So these two little pieces right here, maybe they seem kind of obvious. I didn't write them down directly just because they amount to moving around parentheses and just using the definition of the additive identity. But if you're not following on any part of it, that is, I guess, an important step that it is good to spell out in full detail. So, this seems like an obvious fact that you want to just say, well, duh, like, of course that's true. But we don't automatically know it. That's the point. That is the point of a lot of this intro stuff, is that, hey, get rid of your idea that everything is just lists of real numbers, right? It's kind of obviously true that this is the case if you have a list of real numbers, but if you get rid of that assumption, you should get rid of the rest of your idea that you understand how the things work, because you're not even 100% sure of what stuff you're talking about. That is, if you go back to the definition of a vector space, this big laundry list right here, I claim that if you have only ever seen lists of numbers before as vectors, then it maybe is not clear what sorts of things fall into the category of sets with two special distinguished maps that satisfy certain compatibility conditions. What sort of things are those objects, right? I'm imagining, have not probably got a sense of what all of the different things that could satisfy this type of a condition are. You know at least about one of those things, which is lists of numbers. That's what you've been exposed to so far, but do not assume that everything that you know about lists of numbers carries through to all other objects that satisfy those same properties. Some of them will, other ones will not. So let's see what else we can do. We'll begin to encounter some of the pathologies a bit later on, but for right now, we're just trying to be thorough, and this kind of style of argument may seem a bit pedantic initially, but it is really good practice, and I hope you don't gloss over it. It will save you a lot of heartache in the long run if you get used to trying to prove basic facts that you want to take for granted. If you don't take them for granted, which you shouldn't, because we don't know that they're true yet, and you actually engage with trying to prove them, your life will be much better when we get to proofs that are actually difficult, right? When you take your time proving the easy stuff, you get to see how the basic parts under the hood work. And if you understand really well how those basic pieces work, then we start to see them put together in complicated ways. It won't feel nearly as bad. So here, let's prove this fact that I keep saying. So far, we are just using this as notation. Let's prove that the additive inverse of V is indeed equal to the additive inverse of the multiplicative identity of the field scaling V. So let's prove this fact. All right. It's easy. Here we go. V plus the additive inverse of the multiplicative identity of the field scaling V is certainly equal to the multiplicative identity of the field scaling V plus the same thing as we had before. So this piece right here is just carrying through on that line. All right, cool. Now we're going to use distributivity in the backwards direction. That is, from this step right here, if I distributed these guys on through, then I would get back the previous line. Okay, cool. So 1 plus minus 1, that is the multiplicative identity plus its additive inverse, gives me back the additive identity. Oh, cool, okay. So now I'm scaling the additive identity, or I'm scaling V by the additive identity of the field, and that gives me the additive identity of the vector space by this result we just proved right here. Huh. Awesome. This piece right here comes from the previous theorem. All right, sweet. So what do you think of that? Hopefully, that feels like a kind of satisfying payoff. Maybe not, but if you zoom out, wow, we did a whole lot of different colored boxes worth of content right there. And we built up to something that hopefully you intuitively wanted to be true from the beginning, but I hopefully have convinced you that these things that you intuitively want to be true are not necessarily super easily reachable results, right? Not that like any part of this was terrifically hard, but look, we had to build up kind of a lot of different steps to get here, right? So we had to make sure that we had a unique additive inverse, right? Otherwise, maybe in some cases you would have minus V. Minus V might refer to two different things if that weren't the case, and maybe one of them would be equal to minus 1 times V, and the other one wouldn't, right? So we had to prove the uniqueness of an additive inverse in a vector space. Then we had to prove that if you scale a vector by the additive identity of the field, you get back the additive identity of the vector space. And then we had to put it all together to get back that, hey, this unique additive inverse is indeed equal to this particular scaling of V. So something that seems obvious, we had to build kind of a lot of machinery to get there. We're going to do a whole lot of this at the beginning of the class. We're going to build out things that you're used to taking for granted as true. And like I said before, the point of it is so that you start to get familiar and comfortable with the basic building blocks of what we're going to use in this class, so that when they start to be put together in more complicated ways, it doesn't feel terrible. And yeah, right on. So that's all we got for today. See you next time.
Stay away from me. Just stay away from me. Because right now I can't talk to you. Just stay away.
You're mad at me.
Stay away from me. Don't say a word to me. I don't want to talk to you right now.